Okay, Mr. Worth, this is my electrostatic reassessment, and this is me, Usman Najam. So this is the formula that we're going to start out with. Electrical potential equals work, or change in electrical potential energy over units of charge moved, which can also be expressed as V equals W over Q. And you can find this in the reference table. So this is the first question that's going to use this formula. A potential difference of 10 volts exists between 2 points, A and B, within an electric field. What is the magnitude of charge that requires 2 times 10 to the negative 2 joules of work to move it from A to B? So we start out with a formula which is stated above, V equals W over Q. And we want to isolate Q by itself. So first what we got to do is multiply Q by each side. So we get VQ equals W. And then we want to once again get Q by itself. So we divide each side by V, which results in Q equals W over V. And then we substitute in 2 times 10 to the negative 2 joules, which is given, and then also 10 volts on the bottom for V, which is 10 volts, which is given. And once you express this, it equals 2 times 10 to the negative third coulombs. Okay, so this is another example with using the same formula, but you substitute the things differently. So a proton is moved through a potential difference of 10 volts in an electric field. How much work in electron volts was required to move this proton? So it's once again V equals W over Q, but this time you just multiply Q over and you get the formula VQ equals W, which is what you need to use to find W. So W equals QV, which Q will be 1 elementary charge as given, and then 10 volts for the V, which is given. W equals 1E times 10 volts equals 10 electron volts, which is the answer. And then this is a more like a hands-on thing where you just need to know it. So an inflated balloon has rubbed against a person's hair and touches a neutral wall. Which diagram best represents the charge distribution of the balloon on the wall? So the first one shows all the negatives on the balloon go to the right side, and the wall that's closest to the balloon is positive and mixed negative. 2 shows negative on the side closest to the wall for the balloon, and then positive all on the wall closest to the balloon. So that's most likely going to be correct, because once again opposite charges attract while same repel. So a negative is attracted to positive, and the negative repels a negative farther away. Then 3 shows that negative is, well, the balloons are all the same, positive on the left side and negatives on the right side. So the difference between the wall is that the positives are on the top and bottom and negatives are in the middle. And that's probably not going to be right, because positives should be the only charge that's on the wall closest to the balloon. And then here this is the out of all of them the most wrong, because all the electrons are supposedly being attracted to each other, which wouldn't happen. So this is more defined. So 2 would be correct. The negative charges in the balloon repel negative charges on the wall, which causes positives to be on the front. Okay, this is something that I found unique, and it might help you understand electrostatics better. So this is the formula for force for electrostatics, which is Q1 times Q2 over R squared. For gravity, the force is Fg equals G M1 M2 over R squared, which is unique because both of them use like Q1, Q2, M1, M2. 2 of the same thing, a constant, which would be K in this one, and big G in this one, and then R squared is on the bottom for both. Then 2 equations for field strength, E equals Fe over Q, and then E equals KQ over R squared. And then field strength here, G equals Fg over M, and then big G M over R squared, which again is pretty close. And then both of them have their own constants, electrostatic constant and then gravitational constant. And the major difference between these is obviously the gravity is in one, and that gravity can only attract, while electrostatic can both repel and attract. Okay, now I'm going to show you a very important law. It's Coulomb's law. So Coulomb's law states that magnitude of electrostatic force Fe between 2 objects is equal to a constant K multiplied by each of the 2 charges, Q and Q2, then divided by the square of the distance between the charges, R squared. K is known as electrostatic constant. Fe equals K Q1 Q2 R squared. That's the formula more simplified. So 3 protons are separated from a single electron by a distance of 1 times 10 to the negative 6th meter. Find the electrostatic force between them. Fe equals, this is the substitution when you just substitute everything in. So you got the K by looking at the reference table, the first page of list of physical constants. So it's right there. Electrostatic constant K equals the number. And then you get 4.8 by realizing that there's 3 protons, and as I'm going to show below, 1.6 times 10 to the negative 19th is the 1 elementary charge. So each proton and neutron will have an elementary charge, and as shown here, since it's 1 electron, it's negative 1 elementary charge, and then it's 3 times 1 positive elementary charge, which gives you 4.8 times 10 to the negative 19 coulombs. And then on the bottom, the distance is given. And then once you go through this, you get Fe equals negative 6.9 times 10 to the negative 16 newtons. Okay, this is electric field lines. These are once again things you just have to know. You don't really look at the reference table. So what you need to know is lines point away from the positive charge and always towards the negative charge. So as shown here, even when there's only positives, it's always pointing away. And let's say that those were negatives, they'd be pointing inwards. And then 2, the lines never cross, and the stronger the field, the closer the lines become. So naturally, as the lines get farther away from the charges, they become farther away. And this shows the relationship between a positive and negative charge, how the positive charge goes to the negative charge. And the positive charge, the one all the way to the left, that charge is going all the way to the left because it would probably another negative charge over to the left. Okay, so this is what I was talking about before. What is the value of 1 elementary charge? It's 1.6 times 10 to the negative 19 coulombs. So knowing that, you have to realize that you can't have a fraction of that. So 3.2, 4.8, 8, they're all divisible by 1.6, and which is why those charges are possible. And then what isn't possible are these 2.4, 3.9, 7.2 times 10 to the negative 19th coulombs, because those numbers aren't divisible by 1.6.